Today is the network layer, and this figure is illustrating what IP stands for. IP stands for inter-networking, and the goal of IP is to be global, to interconnect everything, as this figure is illustrating. IP is in some sense the topic of the entire course, so we'll see in several parts. We will see today the first topics of this module that are listed here. And in fact, unfortunately, we had to see some of them in Lab 1, which were explained to you in the lab documents. Two topics had to come, like network mask and things like address format and IP private addresses that we will discuss more now. IP is based on two very simple principles. The first one is explained here. And it has to do with the addresses. So it may seem like addresses are something not important. After all, any address can be used. But it's true in some networking solutions, but in the internet it is not. So for most cases, the IP addresses are first the address of a communication interface, not of a machine, but of an interface. Most machines have several interfaces. Your PC has certainly an Ethernet and a Wi-Fi interface, and a few others that we will see when we do tunnels and things like this. Each of these interfaces has an IP address. And the second most important thing is that the IP address is structured to reflect where the system is in the world. So an IP address has some topological meaning, which is roughly the same as the geographical meaning, but not exactly. What I say topological means if you are inside the IP network of IBM, for example, you will have an IP address that tells the rest of the world this system is within IBM. Now, where in IBM you are might be difficult to know because this is a global company. If your IP address is an IP address of EPFL, then we know you're in Switzerland. In that sense, it says where we are, but it might not be strictly geographical. Every packet contains the IP address of the destination. Seems obvious, but it's better to repeat it. And every system has a forwarding table, which is practically always also called routing table. And the main keyword performs longest prefix match on address destination. What does that mean? I'm illustrating this on this figure. This figure is showing very abstract views of IP addresses with things like A.B.H. Of course, you're familiar with them. They are more likely to seem like 128 dot something, but let's simplify things by having those namings. Assuming Lisa has an address A.H1 and wants to send a packet to Bart that has address B.D.H2. B.D.H2 means that there are 3 blocks in the address. How do we know where the blocks are is impossible to know if I give you just an address. It will be given by out-of-band information, and in particular with the subnet mask and by prefix length in the routing table. For the time being, let's examine what will happen when this packet comes at router R1. Then the router has a forwarding table that says, that can be this one, for example. This B.star output 2 is again a very simplified view of a routing table. In the labs you will see all the contents and the detailed format of a routing table. As a first approximation, we can think of a routing table as having the information, destination, where to go. Here the destination is B.anything, and where to go here in that case is output port 2. In most practical cases, it's not an output port that is written, but things like the ETH0 or ETH1, the name of an interface, and further information. And it also has another line in its routing table, this one, that says anything that starts with A goes to output port 0. Now when this router receives the packet, it does a longest prefix match, which means it tries to match the destination address to all the entries in the table for which there is a match. If there are several, it will take the longest. Here there's only one, B, so the packet goes to output port 2. When the packet comes at router R2, then there are 2 lines that match, B.D and B.star. Star means anything here. And the longest is b.d. Longest means more specific. So the more specific is used, and it goes to output port number 2, which is the correct destination here. This is how IP forwarding works. Second principle, the combination of LANs and IP. What I said so far, IP principle 1, would make the internet simpler if there would be only that. Now there is a second principle, which comes from history, and is essentially saying that don't use routers inside a local area network. What does that mean? Well, it means, for example, if B has some data to transfer to E, both B and E are on the same local area network. They're connected to the same Wi-Fi base station in this case. Then the traffic flow should not go through any router. It should go directly through the base station to E. Now, I'm assuming the Wi-Fi base station is not playing the role of a router here. And similarly, if W has a packet to send to P, and they're both connected to an Ethernet concentrator, there's no router in this environment. There's one to interconnect the red and the blue LANs, but there is none inside each of the LANs. Then the flow from W to P should not go through the router. But of course, if W has some packet to send to E, W and E are not in the same local area network. We need a router in between. That's IP principle number 2. Between local area networks, between subnets, use routers, and inside a subnet, don't use a router. I just realized I forgot to start the clicking software. So I will need to do a small interruption. Okay, let's take risk. Aha. So I probably have a all those things running, right? Okay, none of them is here. Okay, we'll do this first hour without clickers, too risky. Sorry for that. Let's restart. Okay, so far so good. Let's do without clicker. Here's a small test. It works also with raising a hand. We observe a packet from W to P at the point 1, the circled point in black. Right? Which IP destination address do we see? So we observe it here.
Should it work already?
No, the clickers don't work for this first hour. So they will work tomorrow. We'll use Windows 7, not Windows 8. Okay, so who says 1? No, it's not anonymous, right? Who says 2? Who says 3? And who doesn't know? Okay. Correct answer is 1. That's just to clarify, although we don't need a router, we don't need IP to communicate within a LAN, but still we need it. We will put IP addresses, that's a paradox somewhere. TCP/IP communication always requires IP everywhere, even if there is no router, which in some sense means it could be non-needed. There are protocols that work without IP. They tend to become obsolete, but there are a few. And the main reason is, you can guess why. If you would not need an IP address when the destination is in the same subnet, that means the packets you're creating depend on where the destination is, which is something that the application doesn't know in principle. So if we want to make things always the same, we put IP headers everywhere. So the Internet Protocol, by the way, this principle number 2 explains why it's called Internet and not the networking protocol. Internet literally means interconnection of networks. So the true networks at the beginning in the 70s and 80s were the LANs, the local area networks, and IP was made to interconnect different local area networks. Now this is obsolete. I mean, we could forget the I. IP is really the networking protocol, but the weight of history still carries on. An IP address is, in principle, unique across the world. I say in principle, it's important to understand the principles, but it's also important to understand that they can be violated. You will not go to jail if you violate the TCP/IP principles, but it's important to understand that you are violating a principle or not when you do something, right? If you violate a principle, probably something wrong will happen unless you fix the consequences of the violation. So we will start with the principle. A bit later, we will discuss a few typical cases where we violate the principles. At the end of the lecture, we'll see one. So as a first approximation, an IP address is unique across the world. And as we saw last week, there are 2 versions, IPv4 and IPv6. Some terminology. A router is an intermediate system of the IP layer. Intermediate system means a system that handles data for which it is neither the source nor the destination. So it's working for someone else. The opposite of intermediate system is end system, and typically in the IP terminology, it's called a host. Even though the term hosts might mean a PC like this one, but it might mean any system that is acting as an end system. Now let's dive into the details of IPv4. The main difference between IPv4 and IPv6, practically the only difference, the only semantically important difference is the address. IPv4 address, we've seen them already in Lab 1. The only annoying things about the address is they can show up in at least 3 different formats: dotted decimal, hexadecimal, or binary. The computer sees binary, and you see here the mapping, the blue circles. 152 is the decimal notation of 98, which is often read as 98, although that's a bit misleading. It's not the number 90 plus 8, it's 9 times 16 plus 8. Right? And in binary, you have this long, tedious sequence of 1s and 0s. Most of you are familiar with binary decimal and hexadecimal. If not, it's your last opportunity to become familiar. Mapping from binary to hexadecimal is simple. and that's why hexadecimal has been invented. Hexadecimal is the human-friendly way of writing binary numbers. It's much more human-friendly than decimal. The mapping goes by grouping 4 bits, make one hexadecimal digit. Binary to decimal is tedious, and for that you have calculators. Important to remember are the special cases. All ones, 4 bits equal to all 1, that's 15 in decimal, and 8 bits is 255, things we will find common places. Hexadecimal is usually written in small caps, although you find in the past it was written in uppercase. Sorry, it's written lowercase. In the past it was written in uppercase. Today it's considered good taste to write it lowercase. Here's an example of a network that we've seen already. We'll use it to zoom on a few examples. In particular, we'll zoom on what? We'll zoom on this router here that is in the middle of the network. Something that routers have to do is to do this longest prefix match. So they have to know where are the star that we've seen in the table. This is done by routing in the forwarding tables of the routers what is called the network prefix, or simply indicating how many bits of the prefix are before the star. This is typically written with a slash something, for example, /24. For example, if we look at the blue, the router circled in blue, here is its routing table. It contains one line, 128.178.29/24. It means anything that starts, 24 means the prefix is 24 bits. So anything that starts with those 24 bits, meaning those 3 decimal numbers, and anything after that matches this entry. And if you match this entry, what do? You forward the packet where? To this next hop. Next hop is 128.178.102. What is happening here? We see that this is something that is sent to this network, the green network. When we are here and we send to the green network, we send to this router. So the next hop in this case is the next router to send to. The following line is 128.178/16, which means anything that starts with 128.178. And then it goes to the interface 103, which is this one. Okay. So it means, and so this is the second table entry. Let's discuss in a second what it means. The third table entry is 0/0. 0 means star. Means anything matches this line. There are 0 bits. So it's the default route. Anything, any address matches this line, and if you match this line, you go to the interface which is indicated here, which is the red circled router. Now, what does that mean, those 3 lines? Well, because we do longest prefix match, it means if we receive a packet, we analyze the destination address. If the destination address matches the first line, we go to lemma. We go to this green router. We go to this direction. Otherwise, if it doesn't match the first line, we look at the second line. So, for example, if we have a packet to 128.178.182.1, it will not match the first line. It will match the lines 2 and 3. We look at the longest match, which is the second line, and we will go to this router. So line 2 is anything that is inside EPFL, or the wired network of EPFL. The wireless network has a different prefix. Anything that is within the wired network of EPFL goes in this direction, except the first line. And then the third line is matched by anything that does not match the first 2, because we do longest prefix match. For example, if I have a destination that's outside EPFL, I will match only 00, and I will go towards the backbone of the switch network. Switch is the internet service provider of universities in Switzerland. So if I have an address that's inside EPFL and not specific to the green network called Lima here, I will match only the second line. I will match also the third line, but since the third is a shorter prefix, we don't consider it. So this is how the routing tables are written in practice using this slash notation. And this slash notation is used everywhere when we want to express a prefix. So we typically write something which might be longer than the number of bits, and then the slash something means forget anything longer than this number. This notation is used in this column where I explain some of the special addresses used in the internet. One very important special address called the loopback address is 127.0.0.anything. In practice, the anything is always 1. And it means this host. And loopback means it's not just this host going through outside and back inside. It means don't go outside this host. And this is typically used for debugging. When you're writing a program from A to B, then you can write a process A and a process B inside your machine and put as destination address, a destination address inside the machine. It's used for other purposes that we will see also. We have encountered last week some of the private addresses. There are 3 blocks of private addresses. Private addresses means 2 things. First, they are not public, which means they're not expected to be seen on the public internet. If a router at Swisscom sees a packet called destination address 10.something, it will discard the packet. It doesn't know what to do with it because this is not a publicly valid IP address. And the second thing is, because it's not publicly valid, you can do with it whatever you want. So you can use those addresses without anybody giving them to you. IP addresses are given to organizations. So the 128.178 IP address block is given to EPFL. Another company is not allowed to use them. If they do so, it's some kind of cyber attack against EPFL. In contrast, all those private addresses can be used by anybody. So that's very convenient, in particular because you can use them without asking anyone. So typically all home networking devices uses this last block that I've circled here. And you don't need to ask permission to anyone. Of course, when you have private addresses, the idea is to build a private network. For example, if you're a dentist's office, you have 2 or 3 Macintoshes, 2 or 3 printers, and you're not connected to the internet, then you can use those addresses to connect your Macintoshes to your printer. Right? But there is a problem to connect this to the internet. If you cannot connect to the internet in principle. We will see how to tweak a bit the principle at the end of this lecture. Other special address that should not be confused with the private address are the so-called link local addresses. They are also private, but they are more private than the others in the sense that routers refuse to forward any packet with such a destination address, even if you're in a private environment. Inside your private environment or inside your GNS3 network, you can build a network with 10.something addresses. As long as the routing tables in the routers have the correct entries, it will work. So you can build your own private network. Those ones are considered to be non-routable. They cannot go through a router. And the exact terminology is link local. Here, link is a synonym of local area network. So it means an address that can be seen only between systems that can directly communicate without routers. Why do we need that? Well, it's typically used when to configure an address automatically. We will see a bit later, but you've already experienced that in several places at home probably, that an address needs to be configured in a machine. That will be the goal of Lab 2. And if the address is not properly configured, your machine will not work well. There are tools to automatically configure the addresses. When you connect with your smartphone to your Wi-Fi base station, you automatically get an address from a server in your infrastructure that is called a DHCP server, right? If you allow DHCP. Otherwise, you need to type in your configuration panel the address manually. If none of this works, we would have a problem. The system would not work because one of the principles of IP is any TCP/IP communication requires an IP address. So I'm back with the dentist's office that has his printers and his Macintoshes. He needs to configure IP addresses to all of his systems. Dentists are well educated, so in principle he's able to do that. But if you would like to avoid this, you can use those addresses that are automatic, that typically operating systems as a last resource, when an operating system boots a communication interface, you'll try to see if there is a DHCP server to get an address. If there is not, it will hope that somebody will manually configure it. And if nobody does it, it will use one of those addresses. It will randomly pick one of those addresses and attribute its address to itself. You will do a few ARP attempts that we will explain a bit later to see if nobody has the same address. But because there are 2 to the power of 16 such addresses, in your dentist office case, there's little probability that there would be a collision. So that's the typical use of those addresses. So these are the addresses you will see on your PC, probably, if you boot it and nothing works, no DHCP, no manual configuration. And then, once you have an address, you can work with TCP/IP. Of course, you cannot work in a system that has routers. Multicast are other addresses that we will discuss a bit later. Multicast means group, so it's an identifier of a group, and it has nothing to do with all the other IP principles. We'll discuss it a bit later. And then there is the broadcast address, which is all ones. If you put 1 everywhere in 32 bits, you obtain this fantastic address here. Of course, it's link local. Link local means that's the IP terminology for it stays within the LAN. So there's no way to send a broadcast to the internet, right? That would be too easy to do a denial of service. So if you need to send a packet that's broadcast in a local area network, inside the local area network, you are allowed to send broadcast. And if it's a TCP/IP protocol, you need a destination address. In that case, you put this one, the broadcast address. Of course, when a router sees a packet like this, he will never forward it further to another interface, except if it's a bogus router. The IPv4 packet format contains, of course, an IP header, 20 bytes. The main part of the header are the addresses, the source and destination. Yes?
In the broadcast, which computers receive the message?
So the question is, if a computer sends a packet to the broadcast address, which computer will receive it? Well, all the computers inside the same local area network. Okay. So you can do a denial of service inside the local area network by sending lots of broadcast packets, and that's a way to kill a local area network. Yes. Question?
So what if I want to broadcast inside a bigger network like EPFL network?
So what happens if you want to broadcast inside the EPFL network? You can't. And there are good reasons for that. Can you imagine why? Well, if you broadcast to everyone, I mean, you take resources. You take network resources, and you take resources of all the computers. So if somebody in mechanical engineering would send a broadcast thing here, my computer here will receive it while we're teaching. So it has enough reasons to hang because of clickers and PowerPoint and Windows 8. So broadcast would make things worse. So broadcast, of course, is completely banned from anything outside the LAN. So it doesn't work. There are other fields inside the IP packet that we will discuss in due time. The only important field for us here is the protocol. Protocol is the IP terminology for the transport layer stuff. So we expect here to see 2 things. the protocol should be TCP or UDP. There's also another one called ICMP. ICMP is the Internet Control Messaging Protocol. So that is the error codes, if you want, of the IP layer. When I send a packet to a router, and if this router doesn't know how to forward the packet, if the router agrees, it can respond to me by sending an error message. Those error messages are not TCP, not UDP messages. The error messages that are relative to the IP layer itself are all part of the ICMP protocol. You've used it when you've done traceroute or ping. Ping works by sending an echo reply. That's one of the messages that comes natively with IP. An echo reply is handled directly at the IP layer. So you send to a remote machine a reply, an echo request, sorry, not reply. Then if the machine agrees to respond, it will send a reply to you. This is a test message. Here, not an error message, but a test message. Traceroute uses error messages. Traceroute sends a UDP message to a remote destination and limits the number of hops using the TTL field that we will discuss a bit later. TTL field is the time to live here. For example, the first message that traceroute sends is a message to the destination, but saying, do go through at most one router. And if the destination is more than one router away, the first router that receives this message receives a message that has a time to live equal to 1 when it receives it, which means I'm not allowed to send it further. And since I cannot send it further, I drop the packet and I send an error message back to the source, if you are a polite router. Most routers are polite, but not all. For security reasons, those things have been abused, so critical routers that sometimes don't handle those messages. That's why we see stars somewhere, sometimes in the response of traceroute. So if a router is unable to forward a packet for whatever reason, it may send an error message. Then the source that receives the error message may analyze the error message and understand something of what goes wrong. That's an essential tool to debug network configuration, and that's why we've seen it in the first lab. Well, that was for IPv4. IPv6 is the same, but the details are different. Everything is named differently, so it's just terminology exercise. The main difference, as I said, is that the address space is moved from 4 to 128 bits. So the first thing I should have mentioned, in IP, why is it called IPv4? Well, because before that there were 3 experimental versions, version 1, 2, 3, and there's a version number in the header. But don't expect to see version 6 in the header. So an IPv6 packet is not an IP packet of this type with just the version number that has changed. Could have been possible, but that was not the choice. The choice is really to make it a different protocol. So it's not just a different number, although we would expect it to be, but that's not what happens. Perhaps because the source address and destination address are different in number of bits, perhaps that's the reason they choose to make it a different protocol. In particular, and that's the bad news, IPv6 is incompatible with IPv4. So the first thing to really understand is explained on this figure here. If I have a machine, like this PC, that has both IPv4 and IPv6, in fact it has 2 network layers, IPv6 and IPv4. Perhaps some of you remember, if they're old enough, or if they worked in obsolete environments, there were other protocol stacks, like Apple had the very famous Apple Talk, Windows used a novel netware, the DEC machines used the DECnet, so there were other protocols that were not IPv4 and that were different. Today IPv6 is to be treated the same way. It's another protocol. But TCP is the same and the MAC layer is the same. So the network layer is different. Now, being different means that the routers treat them differently. So when a router receives an IP packet, It receives it through Ethernet, for example. Then inside the Ethernet header, we'll come back to the details of this next week, but it's easy to imagine that inside the Ethernet header, there is a protocol type that says it's IPv4 or IPv6 or AppleTalk or whatever. So this machine will know it's an IPv6 packet. Then it will pass it to the IPv6 software for handling, or if it's an IPv4, to the IPv4 software. Those two are separate. There is practically nothing in common between the two. So it can be, if it's in the same machine, it is still morally as if you had two different routers. And then sometimes there will be hosts that have IPv6 only. Because if that doesn't happen, that means we don't need IPv6, right? We need IPv6 because we don't have enough IPv4 addresses. So we expect that in some future, there will be lots of machines that have only IPv6 addresses and only the IPv6 software. Now, there will also be machines that have only the IPv4 because they are old. Perhaps a printer or a door controller or an IP phone in a lift that was not changed since it was installed in 2005, etc. There will be lots of machines that have IPv4 only. The first thing to understand is A and B cannot talk. It's impossible. This guy generates IPv4 packets. They can be routed through the IPv4 internet, but they cannot end up going to an IPv6 machine. B and W can talk because this guy has both. And we will see how the interworking will happen. We will need special tricks to make them work. If we do want A and B to talk, for example, if you are Skyping from A to B, you will need some machine in the middle, a Skype relay, for example, that understands both IPv4 and IPv6 and will serve as a relay. Right? Native communication will not be possible. That's the first bad news, or good news, because it makes the transition to IPv6 a bit tricky. So it's good news for communication systems engineers. Yes?
Just at the slide before, when A and B try to talk without a relay, until where would the packets go until?
Well, assume A sends a packet to B. Well, what can A send? It can send an IPv4 packet. Yeah. So how will, the first thing that A will try is to find the DNS, by going to the DNS server, find the IPv4 address of B. Now, if B is only IPv6, it doesn't have an IPv4 address. So DNS will fail there. You will not find any IP address for this guy. So we'll have an error saying destination does not exist, or whatever your web browser will print. It is as if this machine did not exist. Yes?
There may be a converter, for example, A sends something in IPv4, and then something converts it to IPv6, and that's it. The router sends it to B.
Yes. So the question is, why don't we do a converter? Something that converts an IPv4 packet into an IPv6 packet. And that exists. It's called a network translator, and we'll discuss a bit later. It is possible, and that's one of the solutions that we may use. But there still is a fundamental difficulty, is that when A will try to speak to B, it needs to find an IPv4 address of B. Even a protocol converter doesn't solve that problem. Right? So seen from A, B must be having an IPv4 address. So that's a chicken and egg fundamental problem that the converter is not able to solve. Yes?
Can I put A and B on the same LAN?
Yes. The question is, can I put A and B on the same LAN? Yes, I can. And they ignore each other. Right? It's like if somebody is speaking a language that you don't understand. In this room, if some of you are chatting in Chinese or Turkish, which I don't speak, I will just hear noise, but I will not understand what you say, cannot participate in the conversation. Here's the same. You will burn some of the LAN resources for one of the flows, IPv4, which might reduce the throughput of the LAN, but other than that, they are like, some people say, ships in the night. They don't see each other. Yes?
How is it at this point? Will we at one point see that IPv6 everywhere, or people tend to use more NATs?
So the question is, will IPv6 become
the protocol?
will it be deployed? The answer is yes, but tomorrow. And I've been saying that for 15 years. But we start seeing, I think, last year we start seeing some real IPv6 deployments. But as you may notice, when you will do the lab and continue the labs, most of the things don't work with IPv6 today, seen from here. But all modern machines, whether iPhone, Android phone, PCs with Windows or Macintosh, are IPv6 capable. So, but it's not deployed widely. This is because of what is called the absence of network effect. If I am responsible for a network, for example, I am working at UBS, take a random company, or Nestle, and I'm responsible for their networking infrastructure, right? Should I make everything IPv6 or not? Well, today probably the answer is not, because if I do it, it will cost me a lot of money. I will need to reinstall everything everywhere. Much of the things that worked well with IPv4 don't work well or work differently. It's like if you do a PowerPoint slideshow on Windows and you buy a Macintosh and you expect it to work the same way on the Mac, you'll discover lots of little problems. The same is true when you move from IPv4 to IPv6. So lots of problems, lots of annoyance, lots of cost, and probably zero benefit today because you have enough IPv4 address as a company and as your customers to work with it. The operators might have a different perspective. If you're an operator in a part of the world where you don't receive a block of IPv4 addresses because it's exhausted, then you might deploy IPv6. But for enterprise network today, there's practically zero incentive other than being a good citizen, which is a weak incentive. Question?
So how does it resolve at the moment, the transition phase? Do I send 2 IP packets and the ones I get?
So the question is, how does the transition resolve? Well, don't worry, we'll spend considerable amount of time and click a test on that.